In this session, I am going to explain about network functions. Network functions. So, in these network functions, the topics that I am going to cover here are: first one, introduction about these network functions, and second one, driving point functions, driving point and transfer functions. Third one is problems on these network functions. So these three concepts that I am going to cover in these network functions. So first one, introduction. So in this introduction, the purpose of studying these network functions here is to relate the currents or voltages at different parts of the network. So the main purpose of these network functions here is to relate the currents or voltages at different parts of the network. Here the main these network functions are classified into two types. That is, first one, driving point function. Second one is transfer functions. These two are the network functions here. To understand these driving point functions and transfer functions, we should have the knowledge about the basics. I am going to explain the basics here. So any network can be represented with a rectangular box. So this is a rectangular box. It is a network. Okay. So these networks are classified into two types depending upon the number of ports available for that network. So those two types are: one is one port network, and another one is two port network. What is meant by this port and why it is called as one port, I will explain here. Port is nothing but two terminals together called as a port here. So any network may have two terminals or four terminals here. Here, suppose this is a network. It is a network which is having the two terminals here. It is one terminal. It is one dash, and two terminals together called as a port, or the pair of terminals called as a port. The pair of terminals is called as a port. So for this network, it is only having one pair of terminals. So it is named as one port network. Suppose some of the networks will be there. If the network consists of four terminals or two pairs of terminals, it is one pair of terminal and it is another pair of terminal. So here, this is one port, two terminals together called as a port. It is one port, it is another port. So it is called as two port network. It is named as two port network. And these terminals are named as, it is one dash, it is two dash. Normally the voltages and currents are represented like this. It is V1 and here it is V2. Here this is the voltage, only one port here, so it is V. The current that is entering into the network is I. Here this current which passes through this first terminal is named as I1. This current is named as I2. Here what we need to remember here is these currents are entering into the network. Okay, and here the port at which the excitation is given is named as a input port. The port at which the excitation or the input is given is named as input port. And the port at which the load is connected is named as output port. If the network consists only one pair of terminals or one port, then that network is said to be one port network. So this is one port network. It is having only one pair of terminals or one port. Next point, if the network consists two pairs of terminals, then two pairs of terminals are two ports, then that network is said to be two-port network. So this is a two-port network. Next thing here is I'm going to explain the driving point functions and transfer functions. So let me explain the driving point function first. So first thing here is driving point function. This driving point function relates the currents or voltages at only one port. That means in this driving point function, the excitation and response are measured at same port. So let me explain this. So in this driving point functions, the voltages or currents measured at the same port. That means that may be, these may be that is sorry in this driving point functions, the excitation and responses are measured at the same port. That means if I consider a one port network, this one port network, so this is a one port network. So in this one port network, the driving point function relates the voltages or currents at the same port. That means it is 1 dash, and the voltage here is V, and the current that is flowing through this is I. Here the two driving point functions can be defined here. One is driving point impedance function, driving point impedance function. Second one is driving point admittance function. So let me define this driving point impedance function so that we can understand the definition of this driving point function. So the driving point impedance function normally it is represented with Z of S. So Z of S is equal to, it can be defined as, it is the ratio of voltage at this port, that means at port 1, to the current at the same port, that is V of S divided by I of S. So it is a driving point impedance function. Second one is driving point admittance function. Normally it is denoted with Y of S. So this Y of S is equal to, this is the ratio of current at port 1 to the voltage at port 1. That means the ratio of current transform means I of S, current means only I, current transform means I of S. It is the ratio of current transform at port 1 to the voltage transform at port 2, at the same port, at port 1 itself. Next, so it is about the one port network driving point functions. Coming to this two port network. For two port network, this is the diagram for two port network. Just now I draw this diagram. It is a two port network. It's two port network which is having the four terminals or two pairs of terminals or two ports here. It is 1 dash, it is 2 dash. The current that is entering at this port 1 is I1, it is I2. The voltage at port 1 is V1 and the voltage at port 2 is V2. Okay. So in these two port networks, the driving point functions can be defined as driving point impedance function Z of S, that is, it is at port 1, the driving point impedance function is Z11 of s is equal to V1 of s divided by I1 of s. So at port 1, the driving point function is V1 of s divided by the driving point impedance function is V1 of s divided by I1 of s. What I mean to say here is it is the excitation and it is the response. Excitation and response both are measured at the same port. Here for first port it is measured, and at port 2, so the driving point impedance function at port 2 is different as Z22 of s, that is equal to V2 of s divided by I2 of s. Next, second one is driving point admittance function. Driving point admittance function that is Y of s, and it is different at port 1. The driving point admittance function Y11 of s is equal to I1 of s divided by V1 of s. At port 2, Y22 of s is equal to I2 of s divided by V2 of s. So this is about the driving point functions. So what I mean to say here is driving point functions, it relates the parameters at the same ports. That means here at port 1, V1 of s by I1 of s. That means the excitation and responses are measured at the same port in driving point functions. But in case of transfer functions, that is different. Let me explain about the transfer functions. Here next one is transfer function. So in this transfer function, it relates the parameters, or it relates the voltages or currents at different ports. That means it relates the voltages or currents. That means let me explain this so that you can understand. Here it relates the voltages or currents at one port to the voltages or currents at the other ports. In case of driving point function, at the same ports, but here in this transfer function, different ports. That means, let me explain. First one, voltage transfer function. On this transfer function concept will be existing only for the two-port networks, because the voltages or currents at one port should be related with the voltages or currents at the other ports. That means two ports should be present here. But in case of one port network, only one port will be present. So the transfer function, for the transfer function, two-port network is required. Okay. Voltage transfer function. This voltage transfer function is normally denoted with G of s. Here, this voltage transfer function, it is the ratio of voltage transform at one port to the voltage transform at the other port. So let me expand here. G12 of S and G21 of S, these two voltage transfer functions will be existing. G12 of S is equal to V2 of S divided by V1 of S. G21 of S is equal to V1 of S divided by V2 of S. Let us consider a two-port network here. It is a two-port network. In this two-port network, two ports will be present here. It is one port, it is another port. It is V2, it is I2, it is V1 and it is I1. So it is 1 1 dash and it is 2 2 dash. So in this G12 of S is equal to V2 of S divided by V1 of S. That means this transfer function concept, in this transfer function concepts, this transfer function relates the voltages or currents at one port to the voltages or currents at the other ports. So in this voltage transfer function, this G12 relates V2 of S and V1 of S. This G21 of S relates V1 of S and V2 of S. Next, second one is current transfer function. Normally it is represented with alpha of S. It is the ratio of current transform at one port to the current transform at the other port. So it is the ratio of current transform at one port to the current transform at the other port. Okay. So for the same network, alpha 12 of S is equal to, it is I2 of S divided by I1 of S, and alpha 21 of S is equal to I1 of S divided by I2 of S. So this is about the current transfer function. Next, third one is transfer impedance function. Transfer impedance function. So it is represented with Z of S. So this transfer impedance function can be defined as, it is Z12 of S is equal to V2 of S divided by I1 of S. It is the ratio of voltage transform at one port to the current transform at the other port. Next, Z21 of S is equal to V1 of S divided by I2 of S. So this is about the transfer impedance function. Next, fourth one is transfer admittance function. Is Y of S. So it is it can be defined as Y12 of S is equal to ratio of current transform at one port to the voltage transform at the other port. So Y21 of S is equal to I1 of S divided by V2 of S. This is the concept of driving point function and transfer functions. So let me solve some of the problems on this driving point functions and transfer functions. Here we need to find, there is a question. So here it is a capacitance and this is resistance, this is an inductance. For this I need to find the driving point impedance function. Determine driving point impedance function. Here you know that this is an example for one port network. So this value of it is capacitance, it is the resistance, and it is inductance. So it is having only one pair of terminals, that is only it is 1 dash. So it is an example for one port network. So it is having only either driving point impedance function or driving point admittance function. There will not be any transfer function available for this problem or for this network. Okay. So the driving point impedance function solution for this. The driving point impedance function. Driving point impedance function. So it is Z of S. It is equal to V of S by I of S. So this is the voltage, this V, and this is the current, this is I. So this V and I not given in the problem. So let me draw another circuit which represents draw this transformer network for this. So it is frequency domain network. So it is 1 by CS, it is named as 1 by CS. If it is R, it is R, and if it is L, then it is becomes LS. So this is the frequency domain network. After drawing this frequency domain network, I represent this V of S. It is an excitation, and this is the response I of S. For this input, this is the output that I have taken, excitation response. So I need to find V of S by I of S. So this is totally an impedance. If I assume that it is an impedance, then it will become, it is like this. So it is Z of S, and this is V of S, it is I of S. So V of S equal to I of S into Z of S from this. So V of S divided by I of S is equal to Z of S. So if I am able to find the impedance offered by this circuit, then you can that is the answer for this driving point impedance function. So Z of S is equal to, from this, these two are connected in series. For this series connection, it is in parallel connection. So 1 by CS, it is in parallel with R plus LS. So if you calculate it, 1 by CS, Z1 Z2 divided by Z1 plus Z2. So R plus LS, Z1 Z2 divided by Z1 plus Z2. That is 1 by CS plus R plus LS. And if you calculate it, so R plus LS divided by CS is 1 plus RCS plus LCS square divided by CS. This CS will get cancelled here. So Z of S is equal to, it is if I take L as a common here L as a common, it is S plus R by L divided by, if I take LC as a common here, LC, S square plus R by L into S plus 1 by LC. So this L will get cancelled here. So finally what we got here is the driving point impedance function Z of S is equal to S plus R by L divided by C into S square plus R by L into S plus 1 by LC. So this is the driving point function for this problem. Next, let me solve another problem here. It is another problem. Determine driving point impedance function, driving point impedance function for the following network. So I need to find the driving point impedance function for this network. So it is the network same, almost it is same as that of this previous network. Sorry, so these two networks are different. So it is 1 by S, or it is yes, it is 1 by S. So for this I need to find the driving point impedance function. So whatever the network may be, he has already given in frequency domain network. So just you need to find the driving point impedance function. Z of S is equal to V of S divided by I of S. So this is V of S, it is I of S. So V of S divided by I of S is, these two are connected in series. For this it is in parallel. For the total network it is in series. That means 1 by S plus this S is in parallel with this series network, that is 1 by S plus S. So this is the driving point impedance function. Just we need to calculate the impedances. Sorry, this equivalent impedance, that is 1 by S plus S is in parallel with this 1 plus S square divided by S. So that is equal to 1 by S plus S into 1 plus S square divided by S divided by S plus 1 plus S square divided by S here. So it is 1 by S plus S into 1 plus S square divided by S divided by S square plus 1 plus S square divided by S. This S and this S will get cancelled here. So finally 1 by S plus S cube plus S divided by 1 plus 2S square. So if I take the this one here, it is S into 1 plus 2S square. It is 1 plus 2S square plus S power 4 plus S square if I multiply with S here. So this term I can write as S power 4, this one, plus 3S square plus 3S square plus 1 divided by this one 2S cube plus S here. So this is the driving point impedance function for this problem. Next let me solve the other problem for it. If we are going to solve this other problem, let me explain what is the ladder network here. Ladder network. So if the networks are given like this, the ladder in this form. Okay, let me draw the ladder network here. So these ladder networks are normally, it is Z1, it is Y2, it is Z1, it is Y2, and it is Z3, and it is Y4. So this is a ladder network. That means the same network will be repeated here in this form. So this V1 and this is plus and minus, it is plus and minus V2. Okay, and this is VA, let us assume it is VB. It is VA, it is VB, and the current that is flowing through this is, let us assume, IB. And we know that these currents are I1 and this current is I2. Since it is open circuited, we are giving the excitation here, it is open circuited. So in this ladder network, what I am going to do here is I am going to provide the relation between this V1 and V2. In the problems, he will ask to find the transfer function V2 by V1. So I need to find the relation between V1 by V1 and V2. So if I find the relation between V1 and V2, I am able to find the ratio between V1 by V2 or V2 by V1. So in this type of ladder network, I am going to provide the relation between this V1 and V2. So for this, you see, since this V2 is 0, I2 is 0 here because it is open circuited. This voltage VB is equal to V2. That is the first thing. That is VB is equal to V2. Next, this IB will flow like this, and this current IB will flow like this. Because I2 is equal to 0 here, this current will flow like this. So this VB is equal to V2 is equal to this VB is equal to this IB into Y4. VB is equal to V2 is equal to IB into Y4. Normally V is equal to IR, IZ, but sorry, this is wrong. I is equal to V by Z. So I is equal to V into Y here. 1 by Z is nothing but in admittance Y. So here IB, I can write this IB, the current flowing through this is IB is equal to, so V into Y, the voltage across this one is V2, Y here is Y4. IB is equal to V2 into Y4. Next, VA is equal to, the voltage at this point VA is equal to this voltage plus this voltage. This means IB into Z3 plus this VB, or VB is nothing but V2. So it is V2. So IB here is V2 into Y4. V2 into Y4 IB is into Z3 plus V2 here. If I take V2 as a common here, V2, so it is Y4 into Z3 plus 1. So it is VA. Next, so here I1 is equal to, this current is equal to, I1 is equal to this current plus this current. So this current is nothing but VA into Y2. The voltage into the admittance of this branch will give the current flowing through this. So I1 is equal to VA into Y2 plus IB. This current is equal to this current plus this current. So I1 is equal to VA into Y2, this current plus this IB here. So VA value, I know the VA value, V2 into Y4 Z3 plus 1 into Y2 plus IB value here is V2 into Y4. So take the V2 as a common here, V2 into Y2 into Y4 Z3 plus 1 plus Y4 here. So it is I1. Now this V1 is equal to, the voltage V1 is equal to this voltage plus this voltage. So V1 is equal to I1 into Z1 plus VA. So I1 value, that is V2 into Y2 into Y4 Z3 plus 1 plus Y4 into Z1 plus VA is this one. VA is this one. V2 into Y4 Z3 plus 1. So if I take V2 common here, V2 is equal to this Y2 into Z1. This Z1 is to, for this total one it is Z1. So Z1 into Y2 Y4 Y3 plus 1 plus Y4 plus Y4 Z3 plus 1. Just I am taking this video as a common. So I provide the relation between this V1 and V2. Now if you want to find V1 by V2, then this is V1 by V2. If you want to find V2 by V1, then bring this term to this left side so that you can get the V2 by V1. So whenever these type of ladder networks are in the problems, then we need to follow this procedure. Here solve one problem on this ladder network. For the network shown in figure, for the network shown in figure, find V2 by V1. On this network here is, this is resistance, this is a capacitance, and this is another resistance, this is a capacitance. So this is the network here. And it is plus and minus V1. It is 1 ohm, it is 1 farad, 1 ohm, 1 farad. The current passing through this is I1 and the current passing through this is I2. As given, I2 is equal to 0 and plus and minus it is V2. So in this network I need to find V2 by V1 here. That is what is V2 by V1? It is nothing but voltage transfer function V2 by V1. So since it is a ladder network, so I need to follow this procedure. Whatever the procedure that I followed just now, I need to follow the procedure. Before that, I should convert this time domain network into S domain network or frequency domain network. That means this network I can rewrite as is 1 by CS. CS is nothing but C value is 1 here, 1 by S. This resistance 1 ohm, it is 1 ohm, and this is 1 by S. So this is the plus and minus, it is V2 of S, and this is plus and minus, it is V1 of S. It is I1 of S, and this is I2 of S. It is equal to 0. We know this. Now let us proceed with the same procedure. So it is VA. We already discussed that. It is VB. Let us assume this is IB. Now VB is equal to V2. First point is VB is equal to VB of S is equal to V2 of S. Next, IB of S is equal to, so IB of S is equal to the current flow is this is V2 of S into 1 by S. That is V2 of S divided by S here. Okay. Now VA of S is equal to IB of S into 1 plus this V2 of S. So what is this IB of S? It is V2 of S divided by S plus V2 of S. So it is equal to, if I take V2 of S as common here, is 1 by S plus 1, that is equal to V2 of S divided by S into 1 plus S here. So it is VA of S. Now I1 of S is equal to, for this is equal to, this current is equal to this current plus this current. So this current is VA of S into, this is the, actually it is an impedance. The impedance of this one is 1 by S. I need to multiply with admittance. So the admittance value is 1 by S, that is S here. VA of S into S. So this is an admittance, S value. Also, I forgot to write here, this one is also an admittance. IB of S is equal to, this IB of S is equal to V2 of S into S here. This is S. This is not V2 of S divided by S, it is V2 of S into S, this one. So IB of S into 1, so it is into S. So this is, if it is into S, so IB of S is equal to V2 of S into S, V2 of S into S plus V2 of S. If I take this V2 of S as common here, it is S plus 1 or 1 plus S. So I1 of S is equal to, this current is equal to this voltage VA of S into this admittance is S plus IB of S. So this VA of S is this one, V2 of S into 1 plus S into S, plus IB of S here is, this is V2 of S into S. So take V2 of S as a common here, V2 of S. So it is S square plus S plus here another S here. So it is V2 of S equal to S square plus 2S. So it is I1 of S. Now V1 of S is equal to, so this voltage is equal to this voltage plus this voltage. So this voltage is I1 of S, this voltage is VA of S. So I1 of S into 1 plus VA of S. So I1 of S value is, just now we calculated it as V2 of S into S square plus 2S plus VA of S. So I already calculated this VA of S is V2 of S into S plus 1 or 1 plus S. So take this V2 of S as a common here, V2 of S. So it is S square plus 2S plus S plus 1. So it is V2 of S into S square plus 3S plus 1 here. It is V1 of S. Now what I need to find here is V2 by V1. So from this, V2 of S divided by V1 of S, that is equal to 1 by S square plus 3S plus 1. This is how we need to solve whenever this type of ladder networks are there in the problem. Next another problem here is this is the network. And this is the current. This one is I2, that is equal to 0, is equal to 0. It is plus and minus, it is V2. It is 1 farad, it is 1 Henry, it is 1 farad, it is 1 Henry. It is plus and minus V1, it is I1. So for this network, I need to find the network functions V1 by I1, comma V2 by V1 and V2 by I1. So these things I need to calculate. So whenever this type of questions are there, then it is like a ladder network. So for this type of ladder networks, same procedure I am going to follow here. That is draw the frequency domain network or S domain network for this network. So it is inductance, it is capacitance, this is again inductance, this is again capacitance, it is, so it is V1 of S, it is V2 of S, it is 1 by CS, that is 1 by S, it is 1 by S, it is LS, that is S, so it is S, so it is I1 of S, it is I1 of S. Okay, so here V2 by V1 I can calculate using this ladder network procedure. So in the same procedure I am going to follow here. So let us take this is as VA and this one as VB, and the current that is flowing through this is IB. So you find, you see, this is VB is equal to, we know that VB is equal to, VB of S is equal to V2 of S, and IB of S is equal to, same procedure, voltage into admittance. The impedance is 1 by S, admittance is S here. So V2 of S into admittance value is S. Now this VA is equal to, VA of S is equal to this voltage plus this voltage. This voltage is IB of S into this S plus this VB of S. So VB of S already I wrote here, IB of S into S plus V2 of S. Sorry, IB of S. You write this IB of S like this. So IB of S is V2 of S into S, already here it is S is there, S plus VB of S is V2 of S. So it is V2 of S. So if I take V2 of s as a common here, so it is s square plus 1. So this is VA of s. This is VA of s. Now what I need to find I1 of s. I1 of s is equal to this current is equal to this current plus this current. This current is voltage into admittance. Admittance value is s here. So VA of s into s plus IB of s. IB of s. So VA of s is V2 of s into s square plus 1 into s plus IB of s is this one, V2 of s into s here. So take V2 of s common here. So it is s cube plus s plus s here. So it is V2 of s into s cube plus 2s. So this is I1 of s. Now this V1 of s is equal to this voltage V1 of s is equal to this voltage plus this voltage. This voltage is I1 of s into s plus this voltage is VA of s. So I1 of s is this one, V2 of s into s cube plus 2s into s plus VA of s is this one, V2 of s into s square plus 1 here. Now take V2 of s as a common here, V2 of s into this one, s power 4 plus 2s square plus s square plus 1. So it is V2 of s into s power 4 plus 3s square plus 1. So it is V1 of s. Now what I need to find here is V1 of s by I1 of s, V2 of s by V1 of s, V2 of s by I1 of s. So from this equation, let us consider it is equation number 1 and this is equation number 2. Okay, so from equation number 1, or otherwise what I need to find V1 by I1. So equation 2 divided by equation 1, that is V1 of s divided by I1 of s, that is equal to, so V1 of s is V2 of s into s power 4 plus 3s square plus 1 divided by I1 of s is V2 of s into s cube plus 2s. So this V2 of s, this V2 of s will get cancelled. So V1 of s divided by I1 of s is equal to s power 4 plus 3s square plus 1 divided by s cube plus 2s. So this is the first one. This is the first one, V1 by I1. Next V2 by V1. So this from equation 2, from equation 2, so V2 of s divided by V1 of s is equal to 1 by s power 4 plus 3s square plus 1. Next from equation 1, what I need to find V2 by I1. So from equation 1, V2 of s divided by I1 of s is equal to 1 by s cube plus 2s. So these are the things that we need to find for this problem.